Welcome. My name is Shea Brown. I'm the CEO of BABL AI, a company that audits algorithms for bias, disparate impact, ethical risk, and good governance. So I just wanted to make a little recording here talking about Local Law 144. And in particular, I wanted to talk about some of the new rules that have been proposed, and in particular, the scope of what is considered an automated employment decision tool. And so for those who've been following this, the New York City proposed a law or passed a law that requires people who use automated employment decision tools, in particular employers, to audit those tools for bias. And what is an automated employment decision tool? Well, it's a tool which is used to either hire or make employment decisions about people in New York City. And what counts as this sort of automated tool is really critical. Like, what is part of the definition? What they're really targeting here is machine learning is what that seems to be the focus, especially in the new rules. But some sort of tool that could potentially be biased, because as we've learned, these tools can be biased. AI in general does have a tendency to amplify biases that exist in data, in historical data. And so that clearly is a worry. And so what this law is trying to do is trying to make sure that these tools that are getting used to decide whether you get a job or whether you get a promotion don't have these systematic biases in them. And because the scope or the worry rather has been so much on machine learning, what these proposed rules, and these are rules proposed by the Department of Consumer and Worker Protection in New York, they're trying to target or focus, is what they say, the scope of what counts as one of these tools, and not everything is going to count as one of these tools. And so I'd like to sort of comment on that and reflect on this, because I have a personal worry that the way it's being scoped right now in the new rules could potentially sort of leave out a lot of really important algorithms that sort of are in the spirit of what this law is trying to do. And so what I'd like to do is to take a look at these rules and actually try to figure out what they're trying to say. So here, if you're listening to me, I have open the draft of the proposed rules, and these are rules which are proposed. They don't have to be accepted. There's going to be a commenting period, and this is me I can't wait for the commenting period, so I want to talk about this now. And so in front of me here, they have automated employment decision tool. And so the words are automated employment decision tool, or an AEDT, means an automated employment decision tool as outlined in the original law, where the phrase "to substantially assist or replace discretionary decision-making" means to rely solely on a simplified output, like a score, tag, classification, ranking, with no other factors considered, or to use a simplified output as one of set of criteria where the simplified output is weighted more than any other, and to use a simplified output to overrule conclusions derived from other factors, including human decision-making. So I've already commented actually in a previous sort of webinar about my worries with this current definition. In particular, it feels like almost nothing would be counted here. If you're really requiring that somebody's going to overrule a human decision, almost no tools do that. Unless they just sort of filter out a bunch of candidates where there's no visibility at all. So I've already talked about that, and so that's not really what's concerning me. What's concerning me is the language around what are these actual tools. And so let me go down to machine learning, statistical modeling, and data analytics. And so that is a term that's core to what is considered an automated employment decision tool. And so it has to use machine learning, statistical modeling, data analytics, or artificial intelligence. And so This says machine learning, statistical modeling, so on and so forth, means a group of mathematical computer-based techniques, which seems obvious, that generate a prediction, meaning an expected outcome for an observation, such as an assessment of a candidate fit or likelihood of success, or that generate a classification, meaning an assignment of an observation to a group, such as a categorization based on skill sets, attitude, that sort of thing. Number two, for which a computer, at least in part, identifies the inputs, the relative importance placed on those inputs, and other parameters for the model in order to improve the accuracy of the prediction or classification. And so let me reread that for a second. For which a computer, at least in part, identifies the inputs, the relative importance placed on those inputs, and other parameters for the model in order to improve the accuracy of the prediction or classification. And then number two, and I'll come back to this, but number three rather, says for which the inputs and parameters are defined through cross-validation or by using training and testing data. So they're talking about there are parameters which are going to improve the accuracy. That's two. And for which the inputs and parameters are refined through cross-validation or training and testing data. So they're really being very, very specific here, talking about machine learning, but machine learning in a very specific sense, where this idea of training comes from taking labeled training data, typically, and then feeding into the algorithm and then optimizing parameters in that algorithm such that you get more and more accurate. Okay, which is fair enough, a very good description of most machine learning. However, I have a real problem. I feel like this is being too specific, and there are a number of algorithms that you can think of, a number of procedures that you can think of that would rely on historical data or training data, what we call training data, but don't actually require any training at all or any of this hyperparameter optimization. And so this is what kind of bothers me. And what might actually be easier is if I sort of try to illustrate this. So what I'm going to do is try to draw like how some of this stuff works. And so let me think. So for instance, what I might have as an employer. So let's say I'm an employer. I have hired a lot of people. So people have come into my company. They've submitted resumes, and I am tracking how these people do. And so you can imagine that I have a bunch of employee data. So what I'm going to do is I'm going to make a little table here, and I can record things about these people that might be useful to evaluate new candidates. So I'm going to have a bunch of inputs, and let's say I decide what the inputs are. So there's no computer here. It's just me making some decision. So I'm going to label these inputs as like X, because machine learning, they use X for these inputs. And so we'll just follow that. So I might have X1, I might have X2, I could have X3, X4. And these are parameters. These are something relevant about an applicant, let's say, or an employee. But let's say applicant. So one parameter might be like what their GPA is. Maybe X1 is their GPA. Maybe X2 is something else that's relevant. Maybe it's like the fraction of their work history that had gaps in it. Maybe the people had gaps in employment where they weren't employed for a certain amount of time, and this is like the fraction. So these are two numbers which are kind of continuous numbers in the sense that they sort of vary, the GPA and this sort of gap. So what I'd like to do now is just sort of take these two variables. So I'm an employer, I've employed all these people, and I'd like to take these two variables, and I'm going to assume that I might be able to use them to predict how good of an employee an applicant might be. So why would I do that? Is because potentially these people have been working for me. I'll try to draw a straight line. And I might have reviewed these employees before. So it could be some metric that I'm using to figure out how good that employee is. I'll call this Y. Okay, so this is the thing that for current employees, I have this information, and it doesn't really matter what it is for the illustrations of for this, but let's just assume I have that. Some maybe managers gave some reviews or what their productivity is or something like this, and so I have these numbers for a bunch of my employees, my current employees. Okay. Now, I don't know much about machine learning as an employer. This is me. I'm thinking as an employer now. And I'm also aware of the fact that, New York has this law, which is going to kind of prohibit or make me do bias testing with something that has machine learning. So maybe I'm just going to try to figure out some way of using this myself. And so what I could do in theory is I could sort of try to use these parameters, so x1 and x2. So here, these are these two parameters, and I'm plotting them on this is what we call a parameter space. And so I take all of these employees and I can plot them. And so what I'm going to do is, let's say these employees I have are I have different kinds of employees. I have men, I have women, I have non-binary people, I have people of different races, ethnicities, backgrounds, right? And so these people could potentially be labeled according to that, but let's say for a second that they're not. So they're not labeled, but I'm going to pretend like I know what they are. And so what I can do is I can just start plotting these. And so this is for one group. And each little dot here represents, let's say, a person who is a member of one particular group. Could be men. We'll just make it up. We can do something like men versus women if we wanted to go binary here. And so I could just plot this, and there might be a point out here, right? And this is sort of represents the parameter space of my employees, who are men in this case, who for these two parameters. And then let's assume that, of course, I would also have women working for me. And so let's change the color for a second here. Let's not do pink. Let's just do red here. And they're also in this parameter space. And so I'm just going to draw these here. And what you might notice, and this is on purpose here, is that there's a slight separation between where these groups are in that parameter space. Now, what this is called, when you have a separation like this, this means that one or more of these variables are what's called a proxy variable. So it correlates in some way, and it doesn't have to be a massive correlation. It correlates in some way with some protected category. So in this case, it's gender, right? And it's not crazy to think that this is true for a lot of different parameters that I can think of trying to measure my employees by. And so in fact, GPA and the fraction of time that you've spent unemployed over a period could be proxies for gender, for instance. And so this is not a crazy assumption to make that some of those things could potentially be proxy variables, where there's some difference in the distribution between, especially if it's if I have a small company or there's not a huge number of employees. Okay, so this is assumption number one, that this could exist. Now, I'm not saying it does, and people who do this for a living will try to avoid this kind of thing happening as much as possible. But we know that it does happen, and it's not, and in fact, a big part of what this law is trying to do is try to overcome some of these problems, including things like proxy variables, where there's a difference in these parameters depending on what group you belong to. Okay, so now I need to think. So let's say I'm not aware of this at this point. I'm just plotting this out, and I don't know the red versus blue. In fact, I'm just illustrating to you that there is a difference. with colors. Let's have another assumption. Let's assume that there is some level of human bias. And where does this human bias, where might this human bias come in? Well, it could be in how these employees get labeled within the company. Whatever metric I'm using as a metric of success, of productivity, of advancement and a good fit for the company, whatever that is, there's a real potential that this is biased across any number of lines, including gender, which is the example I'm giving you here. And so let's assume for a second that does exist. Now, this is also not a crazy assumption. In fact, again, this is one of the reasons why these tools, these automated employment decision tools, one of the motivating factors behind having them, for instance, is we know that there are human biases at play. So these two assumptions are not crazy assumptions that they would exist. Okay, so what does this mean? This means that there's a slight offset or a bias between the Y values, these sort of metric that's used to associate quality for male employees versus female employees. And let's not bother with which direction it is. There is a historic direction which is quite obvious. But at this point, it doesn't matter for illustrating this. There is an offset, okay? So I'm assuming these two things, that there is some proxy variables in there, and there is some human bias at play that potentially is causing an offset. So I also don't know this, me as the employer coming up with this algorithm. So I'd like to do some sort of analytics. I'd like to do something clever with this information, this database of information, this long list of employees, historical information of employees. That's a very bad wiggly chart. My apologies. And so, in fact, even in the original law, a database is not considered an AEDT at all. And so I feel like I'm working on good grounds here. I just have a list of data. So what is an algorithm I could use? Well, there's one that is very simple to understand, that even me, a person maybe who doesn't do machine learning, I mean, I do machine learning, but let's pretend I don't, would be really easy to understand. And this is something called K nearest neighbors, and I'll just call it a KNN. Okay, so K nearest neighbors. So what is that? What is this? Right, this is a really simple algorithm. It can actually get quite complex, but the basis of it is quite simple. Let's say somebody comes and applies to work with me. I might have, I'm going to draw a little bar here. I have two pieces of information about this person. I'm going to draw a line. I have sort of X1 and X2, whatever those two parameters are that I also have in the database. They've applied with a resume. I've extracted from that resume some features that I think are relevant for potential future job performance. So I have X1 and I have X2. How can I make use of all this historical data in order to make some kind of inference as to whether this person who's applied for a job might be a good fit and might do a good job when they come and work here? Well, something that doesn't require any training and is very, very simple is this idea of K nearest neighbors. So what you would do is I'll color this person something different. I'll make them orange. What I could do is I would take this person's X1 and X2, and I would simply plot where they are. So let me put them here. Actually, let me not do that. Let's put them up over in the blue area over here so we can tell the difference. And let me get a little more red back here so I can recreate this distribution. Okay, so here is that new person. So I've taken their resume and I've extracted this information, and this is where they are. And I want to know, okay, I have this information. How do I figure out whether they might possibly be a good employee? Well, I have all of these metrics Y here. Now, they're not plotted on here, but the idea of K nearest neighbor is K is some number. This is just some number. Now, sometimes, like 1, 2, 3, 10, 20, something like this. And let's say I just pick a number. So I pick something like 5. What k nearest neighbors tells me to do is to take this x1 and x2, and I'm going to compute for every other employee in my list over here. I'm going to compute the distance this potential employee is from all of these other employees, right? Now, I don't compute it for all of them necessarily. You do, but what I really care about is whatever number I've picked for k, I'm going to take the 5 nearest. So computing the distance is very simple. There's a bunch of different ways to do it. It's a very simple kind of computational exercise to figure out how far away they are in this parameter space. But I pick the number 5. And what I can do is I can look at these 5 nearest employees. And so let's say that I've sort of ranked this list according to how far away they are. And I now have sort of these 5 employees. What I can do is I can look at this parameter y, this metric for how well those employees did. And I can just figure out a way for them to kind of vote on, if I want to guess what's the potential y, I want to make a prediction or an inference as to what's the potential value of that metric for this person who I haven't hired yet. I can simply average those. I can take the median value. There's a whole number of ways to do it. I can weight it based on how far away, like the further away you are, the less it counts in the voting of what that y is. But it's a very straightforward thing to take this and predict this sort of y value. I'll put a little squiggly mark over it to say it's a prediction. It's not a real value. I'm predicting it. And I simply just use the data that I have and I make that prediction. Now, if I land here, right, if this person happens to be up here, because of the proxy variable, that person is more likely to be a male. Blue is male in this case. And so what that means, if there's also human biases, okay, we've made these 2 assumptions that they do exist in the world and they potentially could exist. It's also true that those numbers are going to be biased higher. Whereas if I had another person, let's try to do another color here. Let's just do black. If I had another person where their x1 and x2, x1, x2, might land them sort of here. Let's say, if they have those parameters because of the proxy variable, they're more likely to be a female as opposed to a male. Okay, it's not necessarily true, like there are blue dots over here as well, but statistically, they're more likely to be a male versus female because of the presence of this proxy variable. I do the exact same thing. Okay, I find the k nearest neighbors, in this case 5, and I do the same sort of voting process. And because of the presence of human bias, those numbers are biased down. Okay, now this is the most naive kind of thing you could do. There is no parameter optimization going on here. I chose the number 5. Now, it's true that you can use k nearest neighbors to you can come up with an algorithm to train, what is the best number to get the most accurate results, or what is the best weighting scheme for getting the most accurate results. True that you can optimize those parameters, but right now I didn't optimize anything. And so what I've basically done here would not be in scope for what the New York City is considering an AEDT. However, it has all of the features that we think machine learning have, namely, I'm taking historical data labeled, I'm using it to make and I've modeled the world. So if you do the model inference learning kind of paradigm, I'm modeling the world saying these parameters are important for predicting the parameter y, the metric y. I'm using historical data to make an inference about this y, and I'm learning basically from the historical data to make this inference. Okay, so most people would consider this machine learning. It's very naive, it's very basic, but it would be considered machine learning. But in the current language of the law, this would be out of scope. And more importantly, of course, if the assumptions are true that I put over here, which is not necessarily true, but it's highly likely that this could exist. In fact, we have examples of many proxy variables that are in use. We have many examples of human biases. If these assumptions are true, this is, by definition, a biased algorithm. Okay, so I just wanted to illustrate how the point where if you have a very narrow scope where you're trying to really focus on a particular class of systems that are problematic, there is a worry that you go too deep and you get too specific. And in this case, I think that the current rules are being too specific, because what I just illustrated is a very straightforward, kind of naive process for an algorithm that would be out of scope and is demonstrably biased. And so I think that the department kind of needs to rethink how focused they want to get, because there's a whole class of assessments and algorithms out there that could be potentially excluded, that have all of the features that the city council is worried about when they pass this law. So thank you for, I apologize for the deep dive into some of these systems, but I felt like that I needed to illustrate that there is a worry, and there are clear examples where things that should be in scope are going to fall out of scope. And if this is an example I just came up with off the top of my head, then there's likely to be many, many more. And so I think there needs to be a rethinking of how focused it needs to be, and it would benefit people if the net was cast a little bit broader than it currently is.